Now permutation and combination is one topic, though we have done in school, but historically and me being associated with students for such a long time, I know that this is one topic most students have an issue with. I'll try to make it as simple as possible, but I know I have a tough job at my hand. Let's start with permutation. And before we go to permutation, let's start with what these words denote, permutation, combination and all. It goes like this, that when you have to make only selection, then it is combination. And when you have to select, and then also put them in certain slots, arrange them, you have choices, then it is permutation. Say for example, you have to gift your brother, say, I have a younger brother, you may also have one, somehow we all end up with one, it's a difficult choice, you don't have a choice there, right? So if you have a younger brother, on his birthday, you have to gift him something. You go to a shop, you identify 5 items, amongst which you decide 2 to give to your brother, just being in a generous, we can call it stupid mood. So you decide to give 2 gifts out of 5 to your younger brother. Now, whichever 2 you select, say you select a teddy and a card, right? Or a card and a teddy. It does not really make a difference, right? Arrangement is not involved, it's pure selection. Or you decide to take him out for a movie. So you decide, again in a generous, maybe stupid mood, that I'll take him out for 2 back-to-back movies. A show from 9 to 10, another show from 10 to 11. Okay, when you go to the multiplex, you realize there are 5 movies running in each slot. So what is your job now? First you decide which 2 movies to watch, and then you to decide in which order to watch. 9 to 10, 10 to 11, or 9 to 10, 10 to 11, whatever it is, right? That is permutation. You see, even in permutation, selection is involved. Once you select, then you arrange. So basically, selection is a subset of arrangement. In arrangement also, you have to select to arrange the items. But in selection, you only select. In arrangement, you select as well as arrange. So combination is a part of permutation. Okay, let's start with permutation. And we deal only with permutation, that is basically arrangement. The common formula is NPR. You must have seen it, heard it as a symbol or something. And this is the equivalence of NPR as far as maths go. So n factorial by n minus r factorial. Alright. What does it basically mean? That you have n items, you have to select r and arrange r items. That is what NPR means. Okay. Let's take some numbers and understand this better. For example, there are 10 items, you have to arrange 3. So this basically means 10 factorial by 10 minus 3, 7 factorial. Okay, and I'm sure that all of us are comfortable with the idea of factorial, having done number session and all, so we'll be able to calculate this very fast. Yes, there are some NPR that you must memorize for good, like you just know them, you don't need to calculate them. For example, 10p0. And we can discuss it conceptually also. This basically means you just select 0 items and arrange 0 items. I'm sure you understand in how many ways can you select nothing, reject everything, one way. If you have not selected anything, there is no question of arrangement. So the answer is 1, which can also be seen in terms of formula. 10 factorial by 10 minus 0, which is 10 factorial. So 1. Select 1 item, arrange 1 item. Example, say is a voter. When you go there, there are 7 choices. If you have not decided who to vote for, and you go by name, good names, wonderful name, long names, short names, or you go by the symbol or whatever it is. So if there are 7 candidates, in how many ways can you select a candidate? 7 choices. Now once you have selected a candidate, you don't have an option of arrangement, because one item cannot be arranged. It cannot be arranged in reference to others. So the answer should be 10 in this case. Let's see by formula. 10 factorial by 10 minus 1, 9 factorial. 10 factorial by 9 factorial is 10. Let's say select everything. You have 10 items, select all of them and arrange all of them. Obviously you have to select everything, reject nothing, there is no selection involved, right? Because you are not selecting anything. By default you get everything. And how many ways can you arrange 10 items? Let's see by the formula. 10 factorial by 10 minus 10. That is 0 factorial. Again, having done numbers class, I presume you know 0 factorial is not 0, it's 1. Conventionally taken as 1. So this is equal to 10 factorial. And if I have to select 9 out of 10, which basically means reject 1 item. Select everything bar 1. Then what is the answer? Let's use the formula again. 10 factorial by 10 minus 9, which is 1 factorial, which is equal to 10 factorial. So as you can see, 10p10 and 10p9 are same, which means NPR is same as NPR minus 1. Okay. So 17p17, 17 factorial. 17p16, 17 factorial. 12p11, 12 factorial. 12p12, 12 factorial. Also, if you look at these numbers, 10p0 and 10p1, 15p1, 15, 7p0, 1, So just memorize these numbers. Alright. Now let's understand from where to get these numbers, because I am a firm believer in non-reliance on formula. If you understand it conceptually, you do PNC best when you use NPR the least, and that is the approach that we should try to cultivate. Say there are 3 people ABC. Say there are 5 of them, A, B, C, D, and there are 3 seats. In how many ways can you make them sit in 3 chairs? This is a classic PNC question, a very basic level of PNC question. Just think of it as an event manager. There are 5 persons, all the Khans, and say Hrithik Roshan. Saif Ali Khan and Hrithik Roshan are additional to the 3 Khans. And you have only 3 chairs on the dais. So in how many ways can you make them sit? Now the leftmost chair can be taken off by any of the 5 persons, so you have 5 choices. One of them is already seated, so obviously you cannot take the second chair. Right? So 4 of them are standing and 1 chair is vacant. So any of the 4 can take this chair, so 4 choices. Now 2 of them are seated, 3 of them are standing. So any of the 3 can be seated in the 3rd chair, so 3 choices. Right? Why am I multiplying? This is basically a common concept of multiplication which will be used across topics, and I'll reiterate in different topics also. You must understand, we multiply when the decision making is independent, which means what decision I take in the first case has got no correlation with the other case. Okay? So any of them can sit in the first chair, as well as anyone can sit in the second chair, as well as anyone can sit in the 3rd chair. So we multiply, and therefore we get 60. Right? Now this is something we are all very comfortable with. I'm sure we understand what we have done here. Now let's play around with these numbers. So my answer was 5 into 4 into 3, which is equal to 5 into 4 into 3 into 2 into 1, right? By 2 into 1. Okay, I multiply it with 2 into 1 and divide also 2 into 1. So it's one and the same thing. Which is equal to 5 factorial by 2 factorial, which is equal to 5 factorial by 5 minus 3, 2 factorial. Now if you see, this is equal to 5D, 5 persons, 3 chairs, 5D3, and that is our answer, right? So we understand the derivation of the formula, and not only the derivation of the formula, you must also understand that this approach is as good as this approach, and this approach is far better than this approach, I would say, because when you use formula, sometimes you are constrained by the conditions given in the question, but this approach is independent of the constraint. Whatever be the constraint, you can accordingly modify and alter and use this method. So this is something we should understand properly. Also understand, this is not subject to number of people or number of chairs. The answer does not come as NPR only because there are 5 people or 3 chairs. Whatever be the number of people, number of chairs, this derivation will still hold true. Okay? Alright. Now carrying on from here. Okay. One more thing that I would like to emphasize on this is that NPR is equal to n factorial by n minus r factorial. Right? We all know this. Now if you see, this is equal to n factorial by r factorial into n minus r factorial into r factorial. Okay, which is equal to NCR into r factorial. We'll do this in the combination session, that this expression that I have written here is same as NCR. Okay, what did we discuss at the beginning of the session? Combination is selection, permutation is selection and arrangement. So permutation is not in contrast to combination. It subsumes combination. It is a superset of combination, as we can see here. Combination, when multiplied with arrangement, gives us permutation. And how many ways can you arrange R items? Obviously R factorial, as we saw. So selection of R items by this formula multiplied by arrangement of R items, R factorial, gives us the permutation of R items. Okay, which is NPR, right? Also, you have to understand a few things about NPR or permutation in general. The formula can only be applied if all n items are distinct, all R items are distinct. It cannot be applied if there is some commonality, similarity between the items. Only when all of them are distinct, absolutely different to each other, can we use the formula. Second thing you must understand, formula does not understand constraints or conditions. So formula can only be applied if there is no constraint in the question. So if there is a constraint, first you take care of the constraint and then use the formula. Alright, now let's take some simple examples and understand this in detail. Say it's given that there are 6 persons and 6 chairs. Okay, 6 persons and 6 chairs are given. So we'll do a series of questions based on this. So 6 persons are A, B, C, D, E, F, and 6 chairs are also there for them to be seated. In how many ways can they be seated? Now this answer should come to you very readily. 6 persons, 6 chairs, no constraint, which basically means that we can straight away use the formula. right? So the answer should be 6p6, which is equal to 6 factorial, which is equal to 720. Congrats on getting the right answer. I'm pretty sure all of you got it, right? Now let's come to the real deal. Again, we'll go a little slow, start with simple examples. A sits on the leftmost chair. So my first question is, A on leftmost chair, or A on first chair, whatever you might call it, okay? In how many ways can we do this? Now if A is seated in the first chair, no one else can sit in the first chair. A cannot sit in any other chair, which means A and first chair are taken. As an event manager, as a person taking decision, if someone has already occupied a chair, your decision making authority as well as responsibility goes away. The chair is gone, the person is gone. As far as you are concerned, for all practical purpose, there are 5 persons, 5 chairs. That is what you need to decide now, which means 5p5 or 5 factorial or 120. Do we understand this? So, when you start thinking in terms of actual decision, not in terms of maths question, things become very easy. So, A gone, chair gone, 5%, 5 chairs, 5 factorial, job done. Alright? Now, A never sits on leftmost chair. So now for some reason A has decided, being a very superstitious person, that he will never sit on the leftmost chair. This is a country of superstition, you will have to accommodate all of them. What do you do in that case? You just being a junior manager in an event management company. So what you decide is that you have already calculated the number of ways A can sit in the leftmost chair, which was 120. You already know the total number of ways in which people can be seated, which is 6 factorial or 720. So the number of ways in which A never sits on the leftmost chair will be total cases minus the first case, because A either sits on the leftmost chair or does not sit on the leftmost chair. Nothing else in this universe is possible. So total cases minus A on leftmost chair will have to give me my answer, right? So my answer will be 6%, 6 chairs, 6 factorial or 720, and this answer was 120. So my answer in this case has to be 720 minus 120, which is 600. Okay. An alternative way to solve this could have been that there are 6 chairs. I know A does not sit in the first chair, but my first chair will not be vacant. Someone has to sit. So without A, how many choices do I have? 5. Now remember, originally there were 6 persons and 6 chairs. Non-A, one of the non-A individual has been seated in the first chair. But still now there are 5 persons standing, including A, right? 5 persons standing, 5 vacant chairs. Now no constraint. There was only constraint related to one chair, which has been solved. So now 5 persons can be seated in the 5 chairs in the 5 factorial ways. I go through this again. A never sits on the leftmost chair, but someone has to sit there. Na? Non-A, there are 5 persons. So any of the remaining 5 can sit in the first chair. But if I make one of them sit, I still have 5 persons standing. And I still have 5 vacant chairs. In how many ways can I make those 5 persons sit in these 5 chairs? 5 factorial. Because there is no constraint. So I can simply use the formula 5p5, 5 factorial. Again I multiply, and I hope you understand this by now, that why am I multiplying, which is equal to 600. Okay. A and B sit together. The best way to do questions like this is to take two of them as one unit, right? Now because they are wanting to sit together, so as an event manager I don't even consider the fact that they are distinct individuals. For me they are one headache. What do I do with that headache? I make them sit in adjacent chairs anyway. So say 1, 2, 2, 3, 3, 4, 4, 5, 5, 6. I have 5 possibilities, right? I can make them sit on any of these 5 possibilities. Or alternatively, I can say that there are 6 persons. Now I have clubbed 2 of them together. 2 have been amalgamated to make a giant human being. So there are 5 persons now. 5 persons, and because they will be sitting on adjacent chairs, let's assume that the 2 chairs adjacent to each other is a big sofa, a lounge. So there are 5 persons, 5 chairs. In how many ways can I make 5 persons sit on 5 chairs? 5 factorial. So my answer should simply be 5 factorial. But let's not ignore the fact that I assume A and B to be distinct entity. But the reality is, to be same entity. But the reality is, they are essentially 2 individuals. So whichever adjacent chair I provide them with, 1, 2, 2, 3, 3, 4, they can always interchange their seats. So it can be AB or BA. For every arrangement, it can be AB or BA, right? And if they interchange their seat, the whole arrangement will get a new shape altogether. So my answer will be, when I take them as together, so AB as one unit, say X, then there are others, C, D, E, F. So in how many ways can I make this 5% set? 5 factorial. But for every arrangement, X, the internal arrangement of X, AB can be 2. So my answer will be 5 factorial into 2 factorial, which is 2 factorial. Okay. Similarly, ABC sit together, same logic. So I take ABC as 1 unit, say X, then there are D, E, F. So there are 4 of them, so 4 factorial. Now ABC can internally arrange themselves in 3 factorial ways, not 3 ways. Remember, ABC can internally arrange themselves in 3 factorial ways. So it should be 4 factorial into 3 factorial or 144. Alright. Now say if I ask a question, A always to the left of B. When I say left, don't presume immediate left. It doesn't mean that he sits right next to B in the left direction. It means anywhere in the direction of left, right? Now, how do I answer a question like this? One, I can take the long method, right? Which means I can take cases 1, 2, 3, 4, 5, 6. If B sits here, one position for it, right? He can only sit here. If B sits here, then there are 2 choices for it. He can sit any of these positions. If B sits here, there are 3 choices for it. If B sits here, there are 4 choices of it. If B sits here, there are 5 choices. Okay. Now, understand one thing, that these cases are not simultaneous, cannot occur parallelly at the same time. These cases are alternatives. Only one of them will take place. B cannot obviously take the first, second chair as well as the last chair. It's next to impossible for any human being, generally. So B will either sit here or sit here. And in every position, he will have multiple choices. But he will